Now we're ready to fit the simple linear regression model. So just to recap where we left off, we are trying to find the theta parameters, in this case the slope and intercept, that minimize this mean squared error. And just to help you recall this process when we had just the constant model, visually we could see what happened in the constant model for our different loss functions. Here was our mean squared error and our mean average error, and we were trying to find the theta value that minimized those. So we ended up with our answer here that we could do via calculus, but also visually. And we're going to see, in this case now, we're going to have two parameters. And so the loss function is now going to be a loss surface that we'll be able to visualize in 3D. So let's go to the notebook to see this in action. So we'll be using the notebook titled Simple Linear Regression, and it's in the modeling folder and then the linear regression subfolder. So I'm just going to scroll down. I'm going to define a function in the beginning to help us calculate the correlation, because we'll see later how correlation is used in our model. But just as a reminder, I put everything into standard units, and then I am taking the product of x in standard units times y in standard units and taking their mean. So that's exactly what these two functions do. So first we can actually apply it directly to the data that we had from the parent versus the children height that we were motivating this whole model with. So here's the data itself. It's in the data folder, and when we plot it, right now the way this scatter plot is looks pretty elongated because of just the units, so maybe it doesn't look that linear to you, but we had shown in the previous video that using our graph of averages, it does motivate that a line will be a reasonable model. So let's actually calculate the correlation for this data first. So if plugging it in, I see that I have a positive correlation. It's not that strong. It's not that close to 1. And then we're going to see exactly where that number shows up in a little bit. So to remind you visually what we're trying to do, this code is actually how we created the plots in the last video, where I had 3 possible models. And I was asking you to just eyeball it and think of which one's the best. But we don't pick it just by eyeballing. We now have picked a specific loss function, and we are going to minimize that average loss. So let's look at what that looks like mathematically. And so we're going to calculate our residual, which is the difference between the actual value and your predicted, and then calculate the mean squared error. So that is literally taking the mean of those errors squared. And I'm doing it just for a random slope and intercept. So let's say I just take a line that has slope 1 and intercept negative 0.5. That gives me a mean squared error of 12.16. And so you can visually see that fit. Now what I want to do is play around with those slope and intercept values to see the smallest that I can get this down to. And so for this, I want us to think of, I have 2 knobs I'm turning, either the slope or the intercept. So let's visualize that on an XY axis here. And okay, this height MSE is going to come back. It's exactly what I basically had in the function above. So we could have calculated this earlier, but it's just calculating the mean squared error. To visualize what I'm about to show you, I actually am using some code from a separate library called Data Science. You don't have to install this if you don't want to do the visualization. This just helps in the next few lines of code. So I installed it, and then I imported it, and now I can play around with visualizing how my mean squared error changes as I vary my parameters. So what you're going to see here is, zoom out. Imagine, so this is like my x is slope, y is intercept. So if I come up here, I have a slope of 1.7 and intercept of 22.46. And z is actually the mean squared error that I would get using that slope and intercept. So I can see it's pretty high, right? 5,000. We could see on my guesses down below, I was down to 12, right? So this is definitely a huge mean squared error. And then I can start moving in this space and seeing, oh, that z is going down, that z is going down. In fact, you can think of this visualization as like a topo map. If if you were hiking, and I'm trying to basically find the bottom of a bowl that I'm hiking on. And so this is leading me down to the bottom. Now it's a little bit hard to see because all of these are blue in here, which is some of my smallest values. And you can't tell, like, oh, their Z is 11.6, so I'm definitely getting smaller. And oh, then it popped back up, 11.9. Oh, it was getting, small right there. And so you're trying to figure out exactly where you want to go. And yes, there is a red dot on there that does have the answer. I will show you via calculus how we got it. But it turns out this is going to be the point that has the smallest mean squared error. And let's actually visualize this in 3D before we go on to the calculus behind this. So instead of a topo map, now you're going to see the whole bowl, think of it as a valley. And we are basically imagining you're hiking on this valley because this is your mean squared error, and you are trying to find the lowest point. Now, this looks like a little weird shaped valley. It looks like it's almost like a trough. It has this very flat area here. But actually this function is actually a bowl shape. It just has a very, 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 very gradual slope in this direction, so we can't really see it well on this visual. But there is an actual minimum right there. And so what we were seeing on the previous, or the plot above, was as if we turned this, and we were just looking flat down at it. There we go. And the colors were representing the heights, right? So we were zeroing in on the darker color like this, but then you can see that's how we eventually will find the minimum. And so we want the slope and the intercept that lead me to that smallest mean squared error. Okay, so I told you the answer, and so now we're going to go find it mathematically, but you can see it at least here visually, and it turns out that that is a slope of 0.66, an intercept of 22, and that gives us a mean squared error of 11.4. That's our lowest mean squared error. So let's go back to the slides and see how we got those numbers. So this is the math behind how we solve for this yellow point, the theta naught and theta 1. But technically it's out of the scope of this class because it's requiring, these are partial derivatives, which comes from calculus 3. So really, for your sake, I just want you to have some intuition as to what's happening. To find that lowest value, we actually look for a point where the slope in this theta direction is 0 and the slope in this theta 1 direction is 0. Because you can imagine if you're really at the bottom of a valley, you could kind of turn in any direction and your slope would have to be 0. And that's really what these two criteria are solving for. At the end of the day, there's some algebra to use these 1 and 2 to end up solving for the exact best fit of your slope and your intercept. So you can see the appendix for the algebra, but let's dive a little bit more into interpreting these results. So notice the slope actually depends on the correlation. The slope is the correlation, and then if you recall, correlation is unitless. My slope is in units rise over run, and so we get our units correct here by taking standard deviation of y divided by standard deviation of x. Our intercept here is average of y minus your slope times the average of x. So suppose now we wanted to use this model. You have parents that come in, they have an average height of 69 inches. They want an estimate of how tall their child will be based on your model. What estimate would you provide them? Take a minute. All right, so let's actually plot where these, get a new color here. So you're actually coming in at 69. Basically using the model, we're going to give them, our best guess would be what the average height of children whose parents are an average height of 69. So what's the average height for children of parents that have that input? My little dots there are definitely not straight, so just imagine going straight across. But let's actually plug it in and calculate it. So this model is predicting I'd have 22.46 plus 0.66 times my input, in this case 69. If you plug that in, we get exactly 68. So that would be a great estimate. That is basically the y value from this red line, and that's a great starting point. I'm going to just give us the caveat that this model, right, is based on this sample of data in the blue dots. So if you're worried like, wait, couldn't we have gotten a different line if we had a different sample? And should we be so sure telling the parents it's 68 inches? Or maybe should we give them, for example, a confidence interval around that output? If you're thinking that, I'm glad, because that's what we will be looking at in a future video. So I just wanted to add that caveat that this is great for getting us a good starting point. But number one, it's not capturing any of the spread, right, in the numbers around, or in the values around here. It's just giving me the value on the line. And it's not capturing any of the variation from the fact that this is a sample of data. So I want both of those things in the back of your head for the future. Okay, so here's a regression line. Here is the slope, the intercept, and then the residual. And now we're going to put it back into math notation. So our correlation is already in math notation. But now if we want to think of standard deviation of y over standard deviation of x, we're going to write it like this. Oops. And then the average of y is y bar minus the slope, which we already solved for, times the average of x. So this is what you're going to see that we will frequently just write. And it's the same result, just in our simplified math notation. And then there is your error for the ith data point, also known as the residual. Now I'd like to show you one other form that you may see this least squares regression line written in. So here's the form that we have been using. There's my theta right here, is my theta 1, right here is my theta naught. Now if I just go ahead and multiply some of these terms out, I'm just doing a little bit of algebra in the next line. I'm going to move some things around. And then I am moving this y bar to the left side. I am dividing both sides by this standard deviation. And I'm doing that because if you notice now, I get my equation for the least squares regression line as y in standard units is equal to the correlation times x in standard units, which is actually a really convenient way to remember the equation for the least squares regression line. And I think it also gives some nice intuition about this line. So let's do an example thinking of it this way. They're equivalent, right? So you're fine with either representation. I just wanted you to realize that you could think of it in this way. Suppose I tell you a course has a midterm that had an average of 70 with a standard deviation of 10, and then a final where the average was a 50 and the standard deviation was 12. Then suppose that the correlation between the midterm and the final scores was 0.75, and it was definitely, like an oval shape, so it wasn't some weird patterns in the scatter plot. What would you expect the average final score would be for students who scored 90 on the midterm? And then redo this same question with a 60 on the midterm. So this is a great example of where we could use the least squares regression line as our model. And I'm going to do it in the form that I just showed you on the previous slide because I think it's easiest to think of it this way, where I have y minus my average in y over the standard deviation of y is equal to the correlation times x in standard units. So let's put everything in standard units and we'll see what we're going to get here. So first, I'm trying to solve for what I would expect, like my output y here, y minus, and I'm trying to predict the final. So I'm going to see the average on the final was a 50, standard deviation was 12, the correlation's 0.75, and then I have x, which I'm going to put in just a minute, but let's actually look, x minus 70 over 10. That was the standard midterm score. Okay, let's input a new color here just so you can see. All right, so the x that we're given is 90, right? So now I'm trying to use this to solve for y. My right side here simplifies to just 1.5. So then I have y minus 50 is equal to 18. So now I have that y is equal to 68. And that's what this model would predict. And so you can use that exact same reasoning in part B. And when you work through that, you're going to get 41. So this is just a quick intro example of how we can solve for our least squares regression line. And basically you see all the ingredients that go into it. We need this information about your y, this information about your x, or vice versa, and you need the correlation. And then you can get the equation for the best fit line based on minimizing the mean squared error.